So the point will continue with the definition, quotes and unquotes, so-called neutral pH versus the endpoint's pH. Okay. Now you are familiar with this type of reaction is called neutralization reaction. And I quote, that definition is true for strong acid and strong base because your product pH is 7. So it's exactly half. Okay, but then for weak acids and base, then your endpoint pH will not be 7, even though your solvent is water, right? So because solvent is water, the neutral pH is 7. Yet, for titration, you're going to generate these as product. So strong base, weak acid, the two will react. Quantitatively, we have proved that with a real example that the K of reaction is greater than 10 to the 8. So it is quantitative completely. So the final product at the end point, okay, so equivalence point would indicate these as your product. The sodium anion will dissolve still, so you have this in solution. So the final solution will be, it acts as if you have a base salt dissolve. Notice, indeed, this is your solution. So it's as if the sodium A salt is dissolved in water. Okay? So with this final, you can assume that this final mixture is sodium A salt dissolved. So added to pure water, initially is pH 7 for pure water. But once you add that, this is no longer pH 7, right? Why is that so? Because of this. When this guy added into water, then the two dissolve, then the A minus will react with the H of the OH, and therefore give you this mixture. So the degree, well, this is a weak base, right? It's not sodium hydroxide, right? So in here, it is a weak base. So this is your solution, equivalent to that solution, right? Look at the two. They are the same. Okay, then reaction with water, A minus, will give you the conjugate acid. Conjugate acid. So the proton is intact, it has not come out. Okay? What came out though from water is the OH minus. The OH minus. So once you see this in a mixture, then indeed the solution is alkaline. So your pH is greater than 7. Greater than 7, okay? Because of this case. In pure water, the two are equal, but now, because of this exposure, so this is greater than that. So your mixture is alkaline. Right, so HA, to remind you, is a conjugate acid. So even though it's so-called acid, but it's a conjugate acid, that means that H plus is intact. It doesn't come out, so there's no activity for H plus here. So now, you just use the table value to get the Kb. Why do we call this K, equilibrium Kb? Because this guy is a base. Okay, to get the Kb, you need to obtain it from the corresponding conjugate acid. Okay, the pair, the conjugate pair. So here is how you get the Kb, the two. As long as the mixture is in water, then it's Kw. So it could be a different solvent, then it would be Ks. Okay, will be a different deal. So the conclusion in here is, you memorize this, at the endpoint, the pH is greater than 7. So I might give you a tricky question. What is the pH at the endpoint for this mixed with that? So in the past, some careless student indicate, oh, what's the problem? pH equals 7. That's got a problem right there. Okay. Now buffers. Now the definition for buffer is that a buffer would maintain a particular pH, right? Biological buffer maintain a biological system to a particular pH is important. So follow that definition, then we can look at the titration curve and identify the buffer region. Okay, so look at a titration curve. Now, this is pH, and this is still in solution, right? It turns out that this region is the buffer region. Notice the definition, right? Maintain a pH, so resist change. So this is what happened here. You in this case, you're adding hydroxide, but there's a resistance to change of pH. Therefore, the delta pH is small. So this is your buffer region to fit into the definition. Okay, so a little bit at a time for definition. Then point number 3, the composition. The composition of a buffer will be, you need the conjugate pair. 2 chemicals mixed, okay, 2 external, I call it external chemicals mixed in water as your solvent. So it's going to be a weak acid and it's salt, okay? So example now, so generalized formula for weak acid and generalized. It doesn't have to be a sodium salt. It could be potassium or could be lithium, as long as water soluble. And this is your recipe so far. Okay, then it will dissolve and generate the acidic component and the basic components. So this would be the 2 components responsible for resisting change on pH. So this is your buffer region. How does this work, right? So let's say right? So this is your theoretically your buffer. So see what happened in here. To begin with, then you have HA in this titration. So you are adding hydroxide. So progressively, the HA react OH minus to form that. So what it amounts to, this is the starting material. So this concentration during titration is decreasing, so low arrow. And this guy is generating in the expanse of that, so this is generating. So what is happening in this region is, once you start adding hydroxide, this concentration decreasing simultaneously, and this concentration is increasing. Nonetheless, you have a mixture of that, right? So you have more or less HA and more or less of A minus within this region. And that's why this is a buffer region. So we'll get into that more so. Okay, so this fulfills our discussion points number 3. Okay. Then number 4, it says, the buffer region is right here, now in the middle. Right here in the middle. At this point, you have the 2 concentrations equal to each other. Okay, so with that preparation, if you prepare your buffer, you want to have equal concentrations so that it has same distance to go that direction versus this direction. Okay, and you add more base, so the resistance will be more maximized for base. As you add external acid, then that distance likewise will be maximized for acid. Okay. Any question?